Hello and welcome. Samuel, ici Belleville. J'espère qu'il y a quelqu'un qui m'écoute quand même. Right, so this talk will be recorded and let's get right in. So I'm talking about a categorical approach to probability theory, which for the first time, as far as I know, highlight a very strong parallel with geometry and with quantum probability. So let's see what I mean. In category theory, you can do a bunch of probability theory, and it's quite useful because it highlights a lot of the conceptual stuff and allows you to understand it systematically. Like you can talk about information flow, what's conditionally depend on what, given what, and so on. It's also very graphical, right? The problem so far with the categorical approach is that a lot of the geometry is lost. Geometry of probability theory, as in per this conference, right? GSI is all about this. Here are some more things that are currently missing, which we should address, a little bit more technical. So maybe the last one here is a classical quantum connection. So we should really try to connect more classical and quantum probability, and category theory is so abstract and conceptual that you should be able to do that, right? And another thing is some universal properties are missing. For example, it would be really nice if the product of probabilities was a categorical product, or the product of probability spaces, since we need objects. The problem is that they're not. So you see, we have two marginals here. Then there are many joint distributions that have the same margins. Okay? So uniqueness fails. So it's not a product. But we would like to say that there is a unique, let me say, maximal entropy one, the independent one. Okay? So can we turn that into a natural universal property? Okay, so all three, geometry, universal properties, and classical quantum connections, will be addressed in this work. All right, so let's get started. The most important categorical structure that we're going to use here is called Dagger categories, or sometimes called star categories. If you're familiar with C-star algebras, it's the same star as in C-star algebra, okay? Some kind of transposition, conjugation kind of thing. But I would like to see this in a little bit simpler way. So I want to say a Dagger category is to an ordinary category as undirected graphs are to directed graphs. So let's look at this graph here on the right. You see that here, if you can go from a point to another one, say A to B, then you can also go from B to A. But that does not mean that the points are the same, okay? So similarly, in a Dagger category, if there's a morphism from A to B, there is also a morphism from B to A, but that does not mean that they're isomorphic, okay? It's more like it's a morphism that's kind of undirected. You've seen this before. Take relations. So take a set X and a set Y. A relation is kind of like saying which pairs are allowed, or if you can go from X1 to Y1, but not from, I don't know, X1 to Y2, for example. Okay? But is this X1 to Y1 or a Y1 to X1? Like, is this a relation from X to Y or from Y to X? Well, both, right? You can choose. It's symmetric in a sense. Like, there's this kind of symmetry. Okay? So that's the Dagger category. You can still compose things, you can have identities if you're careful and so on, domain to domain, but there's this symmetry. Very similar to relations, but more like quantitative, it's the category of matrices, where you replace true and false by a number. But once again, is this a matrix from X to Y or Y to X? Well, those of you that had to teach linear algebra might have received a question from a clever student that says, like, in a matrix, are the rows or the columns the inputs? And how do you answer that? Well, it's tricky, right? Why? Because it's a Dagger category. You can actually decide if the columns are the inputs or the outputs. As long as you stick to it and are careful, you can, there's this symmetry within, you can choose. Similarly, and importantly for this work, we have the category of kernels, which is a category whose objects are probability spaces. Here I draw them discrete, but you can also imagine continuous as long as they're like standard Borel, like nice probability spaces. And the morphisms are joint distributions, or like couplings, or transport plans, or measure preserving Markov kernels, hence the name kern. So if you're familiar with like optimal transport, as in like Villani, it's exactly that. Okay, those form a category, and you again have this symmetry, which is like something like a Bayesian inversion, or like the duality of joint distributions. All right. So those are all examples. I hope now the concept of a Dagger category is clear. Anyway, here is the definition. So a Dagger structure is a functor, which turns out to be an isomorphism, between a category and its opposite, called Dagger, which is the identity on objects. So like the dual of an object is itself. But on morphisms, it is not usually, the identity, but it is an involution. It's like if you inverse it twice, you get back to the original. And this in particular, this being a functor means that, let me say, the product of the transposes is the transpose of the product, but you have to flip the order, just like you do for matrices, okay? Okay, so that's a definition. You saw the example, so hopefully you kind of see what it looks like, but what is interesting and less known is that Dagger categories equip our categories with a notion of, I want to say, geometry, okay? And this is usually very, very overlooked, but very, very important. So let's see. In matrices with a transpose, okay, you can say the transpose has some kind of a metric notion, right? Is a little bit like a geometry, but let's see in these other examples what this translates to, which is even more clear. So in the category of vector spaces with a bilinear form, which is related to math, this gives, like the Dagger gives, through the bilinear form, an isomorphism between a vector space and its dual. In physics, like in relativity, for example, this is what you do when you raise and lower indices. Like you have this duality between vectors and covectors, right? And similarly, in Hilbert spaces, this gives this isomorphism with the dual, which is the duality between bras and cats in quantum mechanics, okay? So you might say, well, but those are the same, right? They're isomorphic. So what's going on? It's just the same. Well, almost, as in, you have to pick the metric to say how they are the same. And category theory is all about saying not that just that things are isomorphic or the same, but how they are the same. We have to be really precise about it and use this precision to our advantage. How are these the same? Through the Dagger. Okay? The Dagger encodes this metric and this equivalence. What does this translate to in the Dagger category of probability? That is Bayesian inversion. So you know that probability of y given x can be turned into probability of x given y by dividing and multiplying or conditioning and so on. But there's this duality, right? And this duality is basically the same categorical structure as the one that in physics lets us lower and raise indices. Okay, it's the same structure. All right, what can we do with this geometry? Let's get a little bit more practical. So, as you know, to see in a category what structure is preserved, it's useful to look at the isomorphisms, right? Like, continuous map preserve isomorphisms. You see that because you get diffeomorphisms in your category of topological space. What happens here? So in a Dagger category, you have a little bit more than isomorphisms. You can talk about Dagger isomorphisms or unitaries, which are those isomorphisms where the inverse is the Dagger, like orthogonal matrices. So look at this. So you see a lot of matrices are invertible, but only some preserve the geometry, preserve the angles, the lengths, the inner products, okay? This is what's captured by Dagger isomorphism. You preserve not just your overall structure, but also the geometry. In vector spaces with a bilinear map, with a bilinear form, you get also these more general hyperbolic rotations, for example, like Lorentz transformations, depending on your signature. Or if you just take the right inner products and the right dimensions, like things like symplectic linear maps, like it really preserves your geometric structure on top of the linear algebra, okay? In Hilbert spaces, you get, of course, unitary operators. And in probability, you get some measure theoretic isomorphisms up to measure 0. Again, that's kind of the same thing as a unitary in a certain sense. Let's go further. What are monos and epis? So a mono, like a monomorphism, can be a Dagger monomorphism or isometry if, well, it's a split mono with a section, which is a Dagger. So that's exactly what in matrices gives you, and Hilbert spaces and so on, embeddings or isometric embeddings. So these are like nice injections which preserve the geometry, nice inclusions. What do you get? In probability, you get this thing called a proper kernel. If you're familiar with the work of Sir Jean Pertuis, he actually works a lot with these proper kernels. So that's the Dagger monos in this guy, okay? And the dual is the Dagger epi or quasiometries. These are something like nice surjections, okay? I'm gonna talk a little bit more about this later, but what is important is that this is how you talk about determinism in kernel. So that's how you encode determinism as a kind of a special case of a kernel. What's a deterministic transport plan? A Dagger, okay? The dual to a proper kernel. And also idempotence can be projectors or like orthogonal, but maybe let's skip this for the moment. I'm going to talk about this in a bit more detail very soon, all right? But it's important that this Dagger gives you this notion of orthogonality and geometry, which tells you also something about the probability, in this case, conditional expectation, all right? So that's the introduction. Let's now do something with this. So first new notion, a commutative square in a Dagger category is called orthogonal or independent if these two yellow arrows are the same. Like F Dagger and then G is the same thing as U and then V Dagger. Okay, so let's just call this independent because the word orthogonal and this orthogonal symbol is used already for something else in category theory. I don't want to cause confusion. I'll just do this, all right? So, and also we're mostly interested in squares of maps which are somewhat deterministic, like Dagger. What are examples of this? Okay, so in the category of relations, since we mentioned, this is actually a known thing in category theory called the Bach-Chevalier condition, and makes this a weak pullback. For the people that know category theory, this might be suggestive, but let's focus on the other more geometric examples. So in math, and equivalently also for Hilbert spaces, but let's focus on the finite dimensional, just matrices. Let's first look at the case where D is 0 here, and here we have just 1. So we have the 0 maps here, and here we have not just matrices, but vectors, okay? You see, this is just saying that V Dagger W equals the 0 map, the 0 vector, the 0 number actually from 1 to 1. So you see, this generalizes the usual orthogonality of matrices, of vectors. All right. More generally, if you can view like F and G, or better, the daggers as like inclusions of B into A, all right, or at least if they're not injective, like inclusion of their image, changing possibility velocity, this is exactly saying that they're embedded and their images orthogonally are orthogonal in A, like that, okay? Again, you might have to reparameterize if this is not an isometric embedding, but they're still orthogonal in there, okay? So this generalizes also orthogonality of subspaces and maps. What if D now is non-zero? Well, now D is included this both ways, which commute. So it's like they include, but they have some intersection. But now you see the things that do not intersect are orthogonal, okay? So you see, imagine a book that's opened until 90 degrees, okay? So it's orthogonal except like the bookmark, okay? That's intersecting, that part is in common. But what is not in common, then is orthogonal, okay? We call this relative orthogonality, okay? Orthogonality up to something, some common coarse graining. Now, in probability, for 0 again, this is exactly saying that F and G, if you view them as random variables of non-probability space A, are independent random variables, okay? So the same categorical condition that was giving us orthogonality gives us independence. It's the same thing. And you can imagine what's the equivalent of relative orthogonality? Well, that's conditional independence given the common coarse graining, given the common marginal. Okay? Moreover, we can now make these squares universal. Okay? So you can call an independent pullback a universal independent square. So it's not a pullback, it's universal only among these independent ones. And again, if C is 0, as usual, like in category theory, you call it an independent product. Examples, well, in math and in Hilbert spaces, you don't just get the direct sum of Hilbert spaces as their product, but you get the orthogonal direct sum. So now the universal property, thanks to the Dagger, also includes the geometry, the metric. It tells you which metric. And in Kern, this finally gives us the product of probability spaces. So we finally have a very natural universal property for a product of probabilities. And for pullbacks instead of product, you get the conditional product, the gluing in the sense of optimal transfer. Okay? So the same categorical notion gives us orthogonality and independence. and gives us the desired universal product. All right. It's not the first time that people unify something about linear algebra and independence with the probability notions. So metroids were invented to talk about like linear independence in linear algebra, actually curiously by MacLane, the person that 10 years later will invent category theory. But this was much earlier. Graphoids, much later, were invented to talk about the combinatorics of stochastic independence. And the two things were unified, so probability and linear algebra, by separoids, by David. This still was not using much category theory. The first categorical notion that was used to unify these was by Alex Simpson. I mean, there was some category theory in David, but like Simpson has made this a lot more categorical, okay? And what we did is actually show that these independent structures are actually uniquely determined by some particular things in the Dagger, okay? So that's our contribution, connecting this to daggers and to this geometry, so to say, of category theory. All right, last thing I want to talk about is projections more in detail. So, first of all, you can have in math and, for example, category theory, subsets or subobjects like Z is a subobject of R, and quotients like S1 is a quotient of R. But you see, R and R2 are both. So R is both the subset and the quotient. You can also project. Here, you cannot do that, right? You cannot include the circle back in the real line, at least not continuously or in a group way. Similarly, you cannot project R back to Z. Here, instead, you can. So what's going on? A retract of X is an object E, which you can think of as smaller, but smaller in two ways. So with maps, with an inclusion, okay, and also with a projection back to that, such that if you go a round trip, it's the identity, okay? It's a section. And what about going a round trip the other way? Well, that's not the identity, but it's idempotent. You can think of it as projecting onto this subspace, okay? We call this idempotent split by these two maps, as in the thing on which you're projecting is actually an object of your cat, okay, with the maps that relate it to X. All right, so an inclusion can have different projections, not orthogonal. Equivalently, a projector can have different inclusion, different sections, but only one of them is orthogonal. And you can do that with the Dagger structure. So in a Dagger category, you can talk about a self-adjoint idempotent or projector, again, which has this notion of being an orthogonal projector and being Dagger split, okay? And a Dagger category is Cauchy complete if every idempotent has this splitting. All right, now, in quantum mechanics, when do projectors commute? Well, when things are very related, like you see this orange is a subset of blue, and you see you can project first into blue and then into orange, or project directly into orange, and you have projected directly into blue. They commute. Or they commute when they're very unrelated, position on X, position on Y. You see project first here, and then here is the same thing as projecting first here. So they project when they're very related or very unrelated. What's the generic case? Well, when both happen. And that's exactly our relative orthogonality. You see here, projectors commute, okay? There's a part where they're the same, a part where they're orthogonal, but nothing else. When do they not commute? Well, when they are oblique, okay? So you see, I can project first here and then first here, and then here. See, that's not the same. And when this happens, the composite is not a projection. So you see, I can first project here and then here, and it's not important, okay? So what's the condition? Well, let E and F be projectors in the Cauchy complete Dagger categories, then the projector commutes if and only if this is a projector, if and only if the splitting fits into an independent square. So it's exactly saying that this relative orthogonality is exactly what makes projectors commute, but not just for Hilbert spaces, in every Dagger category, okay? Now, Hilbert gives the example for quantum mechanics, of course, and, well, we have an equivalent for classic, okay? It is this condition, the conditional expectation operators commute. Now, if the common marginal is null, is trivial, this is saying that these two are independent, like conditional expectation is usual expectation, a non-condition for being independent as sigma algebras. More generally, this is saying they have a common marginal and they're conditionally independent given it. And this is a classical analog of commuted idempotence. In the quantum case, okay? Perfect analogy, same categorical notion. All right, I'm gonna stop here. You can find everything in this paper. And if you have any questions, of course, I cannot take questions in person, so please write me at this address, paolo.perrone.math@gmail.com. All right? I hope you found the talk interesting. Well, see you next time. À la prochaine fois. Merci beaucoup.